Good evening, everybody, and welcome. My name is Obi-Wan Pez. This is nSimplex Pachinko, and tonight we're doing more differential equations. Night 11. Going to be talking about linearization of systems and our nonlinear systems that we've been sort of alluding to for the last several streams. So, currently on the line we have enstucky.
Hello.
If you'd like to introduce yourself.
Sure. I'm I'm the host of the Mathematical Creature over at enstucky, or on Twitch, as well as the organizer for No Royal Road, a project for geometry learning.
Nice. And normally we also have Zach at e to the 2i pi, who may drop in later. So we'll see how things go.
You heard from him offsite then?
Nope.
Okay.
But I figure, you know.
Always possible.
Yeah. Alright, so going over to our regular site over on Discord. We're going to start talking with what are some examples of nonlinear terms in differential equations?
So I think we saw predator-prey back in day one, which is that nonlinear? Gotta remind myself what that is.
My daughter's over there making fun of me. Lovingly, of course.
Of course.
All right, so
That looks pretty nonlinear. Something like this. Ooh, that's a that drawing. Okay. That. Yeah, we get these nonlinear terms over here. Nonlinear in this case because I wrote x prime because I was lazy, but that's gonna be. Oh no! Now I erased the problem.
yeah, usually you have to be either super careful or my preferred is using tool number 1 and select dragging.
That's a good hack. So x and y are both dependent variables here. So when you multiply them together, that does constitute a nonlinearity.
Okay. So product of dependent variables is going to be nonlinear. We said that it was going to have to be linear in what? And good evening and welcome, me Machine Rex.
what's going to have to be linear and what?
Yep. So the equations themselves, in order to qualify as a linear differential equation, need to be linear in what?
In the dependent variables.
Keep forgetting my light. And since this is also a differential equation, and it's not just going to be in the dependent variables, but also...
Oh, and its derivatives.
Right, and all of its derivatives. Okay, so I did actually get a message from Zach before stream started. I just didn't notice. Yeah, so Zach will not be available this week, but no worries.
Okay.
And when we say linear in all dependent variables, this also does include terms that have what else multiplied onto it.
Like functions of the independent variable?
Yep. Alright, so anytime we get those, that's still going to be linear. One second. Yeah, alright. Clarification on what works for US plugs. So to anybody who doesn't know, we are an American family. We just moved out to the UK 4 months ago. Just. And we're still dealing with some of the stuff that we brought over. And needing to, you know, not blow the entire circuit and or start fires.
As one does.
Minor details. Okay, so this particular setup here is still acceptably linear, where our derivative for x can have functions of t times x and functions of t times y, as well as our y derivative. So this is still going to be acceptably linear. And if you're saying like, well, how is it linear if it's got an entire function that might be sine of t or t squared or something like that attached to these variables? And we'd said earlier that, and again on day one when we started teaching this, it's linear in all dependent variables. It says nothing about the independent variables. So the independent variables can have these really convoluted functions of those independent variables. All right. Okay, so we have non-linear terms like a product of x and y, and we still have those that are acceptably linear, where we have, again, functions of t multiplied by each of our x's and y's separately from each other. We also have stuff like, you know, x prime is equal to x squared is going to be nonlinear. This one is at least nice and easy because it's a separable differential equation, so we don't have to like stress too hard about it. It's going to at least be decently easy. And if anybody in chat has any questions, please feel free, let me know. There we go. For number 2. Given the following system of differential equations, where would relevant critical points, equilibrium points, asymptotes, and inflection features exist?
Well, we could look for an equilibrium point. I want to set things equal to 0, and I think equilibrium points will do that. If I were to say x prime is 0 and y prime is 0, then that means that there's no motion in either the x or y direction, so I feel like we're stable.
Okay, what else could potentially result in, let's stick with critical and equilibrium points and asymptotes at the moment. Locations for those.
So I guess if I'm thinking about like y as a function of x, then like a critical point would be when y prime is 0, but maybe independent of the x prime.
Okay, so we're going to look for all instances of x prime equaling 0 and y prime equaling 0 kind of separate from each other anyway. And then we'll deal with the consequences of potentially if that's separate or at the same time. But there is another class of features that come about from a slightly different result. So whenever we're talking in like Calc 1, right? What was the other instance of critical points that we were looking at?
I guess non-existence.
Mm-hmm.
So if x prime is has a divide by 0 error.
Yep. So do we have any areas where either x prime or y prime are going to be undefined? And if so, let's find those. Or not and. Shorthand is failing me. English. Okay. So those are going to be our three major classes where we're going to be concerned with finding critical points, equilibrium points, and asymptotes. When I say inflection features, that's going to be what?
Like second derivative is 0?
Yeah. So most of the time when you start talking about inflection features, like some of them are just going to be asymptotes. But others may not be. So we may have multiple different kinds of inflection features, and so we just want to cover all of our bases. X double prime equals 0. Come on. Y double prime equals 0, or X double prime or Y double prime are undefined. Okay. And maybe Machine Rex, to answer your question, this is typically given as one level higher than Calculus 2. Differential equations usually is like the third quote-unquote calculus class that you'd take. It can be taken concurrently or sequentially with Calc 3 in the United States, and likely Canada, but I don't know your particular or their particular numbering system. And linear algebra. So I ended up taking all three of them literally concurrently as they were the same class. Differential equations, multivariate calculus, and linear algebra. 12 credits in one full year.
pretty wild.
It was an interesting experiment, and
Yeah.
I think it would have worked better had I been a little bit more mature. But being 19 years
feel
old,
that.
yeah,
Yeah.
being 19 years old, I don't think I was quite ready for it. And then when we rolled over into the next year, I got mono in February, so I got completely just flattened. The good news was that this class was in the afternoon. The bad news was it was still hard to get there. And I had real big authority issues, so like I was completely intimidated by everybody. Anyway, when is x prime going to be equal to 0?
I don't know. I guess that's going to be when x is equal to y.
Yeah.
X minus y is equal to 0. So.
Right. So from pre-calculus classes, and if you've been taking calculus, Rex, you're right. You say you're in beginning calc, so similar kind of deal here. We're just looking at this and saying, when is y prime going to be equal to 0? Well, when is any fraction equal to 0? It's when the numerator is equal to 0. And then that is going to result in x being the same as y. All right, how about y prime being equal to 0?
Well, x could be 0, or y could be minus 2.
Right, so y prime equals 0 gets us x equals 0, or 2 plus y equals 0, which means y equals -2. And this is a true logical OR. We're allowed to have either of those situations or both at the same time. They are not mutually exclusive from each other, as you might expect from, again, some sort of pre-calculus class, where a lot of times we end up with like quadratics, for example. You've got two different x values which could result in a 0, but that's exclusive. You can only have one or the other. You can't have both at the same time. Okay, could x prime or y prime be undefined?
Looks like x prime could be if, well, 1 minus x minus y is 0, so y is equal to negative x plus 1.
Yeah. Right, whichever way you're used to writing it, or whatever you care about, it's all good. So here we've got our issues. This is where x prime or y prime are undefined. So we have, in theory, a like pure horizontal or pure vertical line. Sorry, pure horizontal or vertical tangent slope. Should be more clear about what that was. And again, x prime or y prime being equal to 0 are good. I'm gonna, yeah, okay. I gotta watch what I say. X prime being equal to 0 is gonna get us a pure vertical line. Y prime being equal to 0 is gonna get us pure horizontal line. And undefined is going to be that there is no particular behavior at that point. There we go. Or we could potentially find a behavior if it just happened to work out. Right, x prime is undefined. We'll figure out exactly what that means in just a minute. Okay, so with that, what is that going to get us? Yes, please, draw a picture. Exactly. Right, so we want to mark individual points where we may have something interesting going on. We have the line x equals y or y equals x, where x prime is going to be equal to 0, so this is our horizontal change, which means that we're going to have what?
Vertically pointing.
Right. So all of our tangents along this line must be vertical, or they can't exist, but we'll deal with that in a second. So if there's any sort of conflict, we can say, like, all right, we need to check this individual point. But generally speaking, this is the behavior along that line. All right, if y is equal to 0, nope, y prime is equal to 0, then we have pure horizontal tangents. So those are going to be just, yeah, horizontal, flat. And where do those occur?
The vertical line x is equal to 0.
Okay. Or?
The horizontal line, y is equal to -2.
All right, so go with somewhere about here. All right, are there any conflicts?
Yeah. They points 0, 0, and -2, -2.
Right, so at 0, 0, we've got a bit of a problem. We don't know whether that is going to be horizontal or vertical tangent because we have both, depending on which thing you're talking about. So we're going to put in just a little note here that these are points that need to be checked. Nope. Alrighty. And if we have x is equal to 0 and y is equal to -2, we notice that these behaviors are agreeing with each other. It's just a horizontal tangent, so we don't need to worry too much about that. All right. If x prime or y prime are undefined, so we have y equals either 1 minus x or -x plus 1. So what's happening along that line? This is where it gets interesting.
Yeah, we just don't really know. So if x prime, so we could just have an existence issue, right? There could be no solution that passes through any of those points.
Right, so generally speaking, we're going to want to take a look at what's going on along that particular line. And also in particular, there are going to be some new points where we're going to have a question as far as what exactly is going on, because we have now conflicts at these particular locations. What are they going to be?
Yeah, at all 3 points of intersection. So 0, 1, 1/2, 1/2,
Probably should have spread this out more, but hey.
And -1, -2. Or what? 3 -2.
Yeah. Right. So we need to look at what's happening at all these places. Now, it could be something completely mundane, where there just is a solution for some reason. It could be more likely that there is no solution at any of those particular locations. It could be that there is an interesting point there, or it could be completely mundane, kind of like a removable discontinuity. So the behavior around it could be absolutely not changed at all. Okay. For that, then, we're also going to extend the question and say, if we wanted to find inflection features, we're going to need second derivatives of these things. Oops. So what would the second derivative of each of them be? Do you want to do one and I'll do the other?
Sure.
Which one do you want, Sticky?
I'll take X.
Oh.
It looks bad, so it's probably better.
Brave. All right.
Yeah, I think that philosophy was wrong, but it's okay.
Yeah, I thought you were 100% gonna say why just cuz. Oop. Oh. That's not what I want.
Nope.
How we doing, Suki?
Hanging in there. How we doing?
Done with mine, but...
Getting
All right.
slightly less cancellation than I was hoping for.
For anybody who's following along, y double prime is equal to 0. We're going to take y prime and take its derivative, so therefore y double prime is going to be equal to... we have here a product rule, x times 2 plus y. So we do x prime first times our 2 plus y, then plus x times the derivative of 2 plus y is just y prime. Then we take y prime and we replace it, and we take x prime and we replace it with our original stuff that we had way back at the beginning. Which gets us a product of x minus y times 2 plus y all over 1 minus x minus y plus x squared times 2 plus y. I then factored a 2 plus y out from both things because if we're going to set this equal to 0, again we want y double prime to be equal to 0, then having a product of stuff is way easier. So factor out anything you can. In this case, our common factor is going to be 2 plus y, and that leaves us with x minus y divided by 1 minus x minus y plus x squared. So if we set that whole y double prime equal to 0, it breaks up into two conditions. Either the first 2 plus y is equal to 0, or the second, that big thing there, is equal to 0. And again, it could be both. So the consequences of the first one is the same as what we had earlier. That was y equals -2 is also an inflection point. So our first derivative is changing its direction along that line. Again, this is generally speaking. It may not end up doing it, but we have to consider the options anyway. And then the big one, here we said that x minus y over 1 minus x minus y plus x squared is equal to 0. I decided to multiply through by 1 minus x minus y, get rid of all the fractions, gets us x minus y plus x squared times 1 minus x minus y is equal to 0. Expand that out, we get our x squared minus x cubed minus x squared y. And then here I said, all right, take all the y terms, move them right, and take all of our x terms by themselves and just leave them where they are. And then factor out the y and divide by 1 plus x squared. So that gets us all this stuff here. We could probably figure out like some features of this, but I don't really care that much. It's going to be kind of a... It could very well factor out x squared plus 1, but I'm not going to do that right now. So, long division, yay! We're going to just graph this and see like where exactly it shows up on our phase plane. There we go. And see if we can see it in the system itself. All right, Stooky.
It's bad. That's all I got.
And that is perfectly fine. Yeah, we got a lot of x primes and y primes.
Just thinking about that first step. It looks pretty good.
Interestingly, there is at least the possibility, as gross as it might be, if you turn this into dy dt and this into dx dt, you could end up with a term that is dy dx.
Right.
And then that would end up getting you
Not so bad.
What was it? 1 minus 2y over 1 plus 2y minus 2x. Yeah, so this is, at least it looks less gross. But at the same time, now this is like its own differential equation, so, and it's not particularly separable. It's still going to be really weird. But at the same time, in this case, we would say, like, wherever the slope of our, like, field is one of these, like, fits on this function, then we would be able to, what is that? Have an inflection point or an inflection feature for x. So yeah, kind of weird and probably a little gross, but what if 1 minus x minus y is equal to 0? Yep, that's also a good point. So we would also say that from the beginning there. Y is equal to, same thing, 1 minus x. Good call. Right, so if this function is undefined as well. So we'd also need to consider that. Okay. Cool times. All right. So these are the features, these are the points where we need to look at stuff. At this point, you know, you could go through and do manual analysis, but we have tools for that. So I'm going to pop over to GeoGebra here. And this is the solution, or this is the phase plane for this particular differential system. So here we have our x minus y divided by 1 minus x minus y, and y prime is equal to x times 2 plus y. So we've got this field here, and we could check all sorts of different initial conditions and say, like, you know, what do these look like if we just kind of move these around a bit, and what kinds of behaviors do we have. You could tell that this is a very complicated sort of system. It's got what looks like here, what kind of behavior? Oh, I'm sorry. Let me... back to Excalibur and post. There we go.
So it's sort of kind of looks like a spiral source at the origin, and then has some asymptotic behavior.
Right, and if you look at where is that? Very approximately, it's probably going to be a half. Right, what does that kind of look like? I'll also post another one here.
Oh, I see. So that's like a saddle.
Yeah. So we have similar behaviors going on, right, in these locations. Similar behaviors to our linear systems. So again, it looks like we've got a spiral source out of 0, 0. A half looks like a saddle point, so it's got behaviors, again, that are opposite to each other. on all four sides of that particular, oftentimes it's called node. So on all four sides of the node, like it looks like our function is moving or being kind of repelled away from that node. Okay, so looks like a saddle point at a half. Any others we can see on there?
One, two. Oh, that's way over there. I don't know what's going on at 2, 2.
Yeah, so -2, -2. If I go like that.
Probably also saddle-like. Looks pineated saddle.
Yep, you can see it better in this one. And based on just even the pictures that I have here, what does it look like is going on at 0, 1?
0, 1. 0, 1. I guess that's also pretty saddle-like behavior. Oh, I see. I have the wrong. No? Okay.
Yeah, learned about initial conditions from Santa Fe Institute. They, of course, is on Chaos. Yep. Oh, we're getting there.
Just looks flat.
Yeah. Doesn't look like anything, so... Just looks like it might be removable, essentially. Where, like, nothing appears to be happening, so is that really what's going on, or... I guess we're just going to have to look at it through the math and see what it says is actually happening at that point. And last one was 3, -2. So if we pull up, yeah, it keeps locking in. My GeoGebra wants to like pick that particular point. But essentially, we can see on this one, there's kind of also nothing especially interesting seeming to go on right there. So we'll examine what it is doing in the math itself. But again, doesn't seem to be doing anything, so we'll also call that possibly removable. Question mark. Okay. So then the question becomes, how can we talk about the individual behaviors in terms of... whoa, nope. Overzealous with my mouse wheel. How can we talk about the individual behaviors that are going on around each of these individual points? I don't know if you have any thoughts in terms of like how this looks compared to, say, Calc 2. I think this is the right question. We'll hang on to that one for a minute. That's probably out of order. Which question did I actually want to ask? Yeah, you know what? Question 5.
Is that... Okay.
2, 3, 4, 5. So linking all this stuff back to power series in Calc 2, each of these features appears to have sort of like a dominant area for the linear system, and again, we'll deal with the math behind it in a little bit, but do you notice anything, I suppose? Or any similarities to the words we use in Calc 2?
No.
Okay. Perfectly valid. It might have been too early. Maybe there's a good reason I put that in number 5 position. Okay. Now, it could also be just my training because, you know, I've been doing differential equations for basically 20 years. But, like, there's something about this one here that I circled with, like, similar to the linear systems, right? That is showing me that there's some sort of behavior which is kind of curving around this particular point, around our 0, 0. And there's going to be a region in which these behaviors are dominant. So we'll talk a little bit more about that as we get to it. But so around what point were our linear systems vectors always measured from?
Around the origin.
Right, so we started at 0, 0. We said from this particular point, we kind of, you know, went out a particular vector, and that was our eigenvector. We said everything was kind of all of our solutions were kind of using that eigenvector as part of its movement behavior in order to transform the matrix, transform our initial x vector to some new vector. So for this one, how might we be able to alter, right? So this is not going to be just a simple x prime equals ax. But how might we be able to alter this matrix system to say, you know what, we need to deal with something that's not on the origin, and maybe we'll just consider like the behaviors that are happening within this small area. Yep, Rex. Yep. Bottom of a bowl is stable, middle of each saddle is unstable. Yep, so we have the different types of equilibria. An unstable equilibrium would be, for instance, if I tried to balance the stylus on the absolute tip of my finger and then just let go up top here. That would be an unstable equilibrium. In theory, I could find the exact location that I could hold this pen and then let go, and then it would be perfectly balanced. In theory. We're not going to trust that that happens very often. It's extremely unlikely that I would be able to sustain that, especially since I have a nice little persistent tremor. So an unstable equilibrium would be something like if we're perched at the top of a hill, if, again, you're trying to balance something on the tip of your finger, or a whole bunch of different ways in which this could be the case. All it's going to take is a minor nudge in any particular direction, and that's going to send this particular system toppling to a different state. And I'm going to asterisk permanently here, but generally speaking, that's true, right? You're not going to get back to this state. This is one of those like entropy type questions where physicists are going to hate me for this. Where like the entropy in this particular system does not want it to remain here. Yeah, bottom of a bowl, or sorry, top of a bowl if you turn it over, right, typically is not going to be particularly stable. The absolute top of a mountain of dirt or something like that. Things that you put on top of it are going to want to fall away from the top. We have the stable equilibrium, which is going to be, again, like the bottom of a bowl of a hill. If you nudge it upward, then it's going to generally fall back right where it came from. And again, generally speaking, a nudge is going to cause it to return to this state. I guess there is a nudge small enough such that, right, it will return back to this state. There is the possibility that we've seen this before. There's another like hill here. If you nudge it far enough, it's just going to go right over and keep going forever downward. But we're just talking about a small nudge from this current state will put it into this state again. Unlike our unstable equilibrium, where a small nudge, even infinitesimally small, will cause this to enter a completely different state. And again, theoretically, permanently. And then we have a semi-stable, where a nudge in one direction will cause it to return back to its current state, whereas a nudge in the opposite direction will cause it to fall away. One example of this might be a if you have like a dam system on a river. if you try to nudge it back uphill, it's going to fall back into this particular like mid, what is that? Spillway, a spillway. So you have a like high river, and then it dumps down into a mid area, which dumps down into a low area. So a nudge upstream will end up returning it back to where it is, and a nudge downstream will cause it to fall away. Okay. So what we're going to do is this concept called linearization. So what we're going to do is we're going to assume that there exists some some vector u, which is going to be equal to and in this particular state, the problem is that we don't have a vector x where this is going to be a linear system. But we did take a particular point that's somewhere way out here, and we can call it, for instance, we can say our initial x at t0 and y at t0 are going to be equal to what we call x0 and y0. I'm sure Stucky is very familiar with this. Use that in every class. All right, so what we're going to do is we're going to say that u is a transformation of our original x vector, which would have just been xy. And we're going to transform it very simply just by moving it. So this effectively causes the u vector to become at the origin of a coordinate shift. So here this is just going to be x minus x0, y minus y0. Right, such that for sufficiently small x minus x0 and y minus y0, really it should be comma. But u prime is going to be approximately equal to, as in like reasonably close, a times u vector. So this is going to be like yeah, so Mean Machine, the way that we're doing this here is Zach, our other member who is not here tonight, originally did a real analysis class in the winter, and both Stucky and I were part of 2 different classes that were running at the same time, one in the morning, one in the after, or was it off days? I can't even remember anymore.
Just afternoon, evening, yeah.
Yeah. Oh, that's right. Yeah, afternoons and evenings. And I was happy to, lend a hand and join in, and turned out there were a lot of people who were very interested in real analysis. So the both of us have taken real analysis at various points, and Zach just wanted to teach it to try to get kind of more practice in this particular style of teaching, and he more or less did what we're doing here, ask a bunch of questions, have a discussion, rather than necessarily like lecture at people, because And then I said I was interested in running a differential equations class, because that is kind of my specialty. I've taken the class a whole bunch of times, and I've taught it 5-6 semesters, something like that, at my community college back in Maryland. Zach is also running part 2 of real analysis in September, which is going to be called Infinite Series. Penn Center is currently running a class on complex analysis, and
I think that might have just finished up, but yeah.
That's right, yes, it did. And is planning another one, question mark, for the spring?
Yes.
Why, thank you, Rex. And yes, here we have, you said the magic word, so we're gonna let you in on, these are the math chads. We have Dawn at Dawn Does Math, Zach at e to the 2iPi Penn Center, Ian Stuckey, Obi, that's myself, at nSimplex Pachinko, Dan at Danny Highway, and Dr. Gold at Actual Education. We all do math streams of varying types. Not everybody has done, is willing to, is going to teach a class necessarily, but we all do some sort of, like, usually homework help, talking about how we would like to teach particular sections and things like that. So there's all sorts of cool stuff out there.
Yeah.
And we're all also attempting to become members of the Knowledge Fellowship, TKF. Several of us have been approved, and the rest of us are on the list. So they're gonna the
I genuinely have no idea what the status of that is for anybody, except that Zach seems to be pretty well integrated.
I have all of the stuff. So Sage sent me a message and was like, hey, welcome to the team or whatever. Here's like all of the things to put in your bio and things like that. But I have not done it. Whoops.
Oh, okay.
But I think they're basically like at the next board of directors meeting, Sage is going to be like, here are the people that we want to approve. And it's going to be passed through. So I get the feeling that, our vouching for each other and things like that are follow Professor Melko. I don't know that one. Interesting. I'll have to look him up.
I'm not sure.
Okay. So anyway, for linearization, we're going to assume that there is a linear system which is centered around x0, y0. And so therefore, for sufficiently small x minus x0 and y minus y0, we're going to get a reasonable approximation for all of those individual, or for that particular system that exists around that point x0, y0. So the next order of business there is to say, well, what is A going to be? Because that's kind of important, right? How do we determine what the transformation matrix is going to be for all of the individual vectors that are immediately surrounding x0, y0? Stuki, I don't know if you have any particular comments, questions, or you know the answer to that one, but
I mean, I'm getting some Taylor vibes here, so I would like to try to write out some Taylor expansions, kill the higher order terms, and pray.
So good news, not today.
Okay.
So what we're going to do for our transformation matrix is we're going to say that the change in any particular direction, so u prime, essentially, you know, how we're multiplying our u vector. So we're going to get our a vector here times our u vector x minus x0 y minus y0. Alrighty. Awesome. Right, the ways in which our rates of change are going to exist are going to be that we want to look at specifically how is x changing in the x direction, how is y changing in the y direction, and then we're going to sum those things up. So how do things change in a particular direction? Let me also... Right. Let me also rewrite our system. Some people may know that I tend to get a little vague when I don't want to give away the answer immediately. So I do always apologize to my co-hosts, because it is perhaps not always a fair question, but come on. Ah. Oh dear. My mouse appears to be thinking that it wants to do something else. It's weird. Alright, anyway. So if our system is going to be written as x prime is a function of x and y, and y prime is a function of x and y, how do we then say, okay, we only want, in our first position, the rate of change in the x direction?
So somehow we're looking at the top row.
Yep.
Or sorry, the top row of the system.
Yep. Alright, so I hope that helps a little. So each of the things that exist in these locations, in each of those 4 locations, are going to relate the rate of change of its row variable with respect to what position it is in the column. So that corresponding variable for our y column. So how might we be able to find our rate of change of a particular variable in a particular direction? Broadly. Or like what other class taught us to do stuff like that?
What? I mean... what?
Sorry, Snooki.
So x prime is how much change there is in x, but it's not... But that's with respect to time. I guess I'm just not seeing how we can get these cross terms. Like, I just... For the rate of change of x in the x direction, I guess I want to plug in x equals x naught, y equals y naught to f.
Okay, and it's perhaps like one layer off, because so we are going to plug in x naught, y naught into... Now, this is not just f. What we're going to do is we're going to look at the... Let me pull up the... I looked something up on... there we go. So this is going to be taking the essentially first order partial derivatives of our rates of change and then applying them to our... Wrong window. There we go. And then applying them to our transformation. So, Rex, this is we're approximating a nonlinear system using linear operations. So even though it's not actually a linear system, we're saying, hey, if we're doing this over a sufficiently small area, it will look linear. It will be ever so slightly off, but it's going to be close enough. So here what we do is, instead of just f at x naught, y naught, it's going to be the partial derivative of f with respect to x.
Huh? Why?
I had a really good sentence and I completely lost it.
Oh, wait. Okay. Respect to x.
So the right? Rate of change of our x variable is just going to be, usually we just call it f. But in this particular case, it's going to be how is like the entire sorry. How is the vector field around that particular point going to be manipulated in such a way that this gets us our linearized system at that particular point? Probably not explaining it well. I had a better explanation somewhere. Sorry, Stookie.
All good.
Yeah, and Rex, you can see when I completely crash and burn.
Okay, I see. I see what's happening here. This is a okay. Because I'm supposed to think about this x minus x naught as being like dx. Right,
Essentially, yes.
right, and so this is so we're trying to write down like the chain rule, right?
I think that makes way more sense, yes.
T is D. Okay, let me pull back on that a second. But fx, so this first term is going to contribute a dx over dt times, or wait, no, dx over dt, but partial of that with respect to x dx. And then dx over dt partial y dy. Right, so that's it still feels like
so I would say yes, this is probably as accurate as we're gonna get for this. But yeah, what we're saying is it's going to be a linear combination.
I'm not afraid of your ghosts, Bridget.
Right, the actual rate of change of any particular vector around this particular point is going to be approximated by a linear combination of the partial derivatives with those respective directions around those individual points. Oops.
I think everyone wonders what they would do if they saw a ghost.
Right, because we can't just consider the rate of change in the horizontal direction, because the system itself is saying that both the horizontal and the vertical change are going to contribute to the overall rate of change dx dt. Does that make sense?
Yeah.
Might be sort of hand wavy, and that's fine. Okay, so we want the linear combination of our f partial with respect to x and the f partial with respect to y at our particular location x0, y0 to tell us what the total overall change is going to be approximated as for each x and y in that vector. So then if we if we do what you wrote down below, right, it should look like this. Right, partial derivatives with respect to each x and y, those are going to be contributed with our, as you put there, our alleged dx and dy, x minus x0 and y minus y0, which again, within a reasonable distance, this particular behavior that we're centering around is going to be dominant. This is kind of in a similar way to when we were looking at like behaviors of functions back in pre-calc, and I always am going to bring this back to pre-calc because that's my specialty, teaching specialty. 15 straight years of it. Right, if you look at a particular factor in a product of a factored polynomial, then within a certain region, each of the individual zeros of that factored polynomial are going to dominate the behavior of the polynomial overall. So as each individual one gets close to 0, then the whole polynomial gets close to 0. So the same sort of thing is happening here, where we're saying, like, as we get close to x0, y0, whatever node, whatever equilibrium point, whatever, there was another good word for it. Sometimes it's a singular point, so not always, but if it's a singular point, then immediately surrounding that point, all behavior is going to be run by that particular system that we're coming across. Okay. So again, this gets us an approximately linearized system that's going to get us something reasonable within a small reasonable distance of that particular point, x0, y0. So with that, what we're going to do is we're going to say, all right, let's take our system that we have here and pretend it's linear and run the same test that we did earlier. So we're going to say, let's take our f partial with respect to x. F partial with respect to y at these particular locations. G partial with respect to x. And G partial with respect to y. And take it and subtract our lambda I and again we say that this is going to be our x minus x0, y minus y0, and we want this to be want this to create a linearly independent system, so it's got to be equal to our 0 vector. And therefore, what are we going to get? Right, we're going to say if this is going to be approximated by a linear system, then we're going to be looking for eigenvalues and eigenvectors. and then we're going to find our approximate solution. All right. Shall we give it a shot?
Sure.
All right, pick your favorite one, and I'll pick a different one and see where we get to. I'm going to take a 3-minute ad break while we do that, just so that we get rid of the pre-rolls and stuff. If anybody else out there has any questions, please let us know in chat, and we'll get back to you in approximately 3 minutes. Alrighty.
Okay.
Which point you picking?
Oh, sure. I don't know. Do you want a sneak preview for me? I don't really know what happens with the removables. Is that like not going to be interesting for our purposes?
I think probably we should leave those out for now.
Cool.
We'll just do the...
I'll take -2/-2s then.
Okay. And I will attempt to do 0, 0, and a half. Probably not in 3 minutes, but whatever.
Decide what's important to me to look at. Do it over here.
Oh. That should be both of them negative there. Alright, everybody, it appears we're back. So what we have here, I was looking at doing the system at 0, 0. We have the partial derivatives of f and g with respect to both x and y in their appropriate rows and columns. So the partial derivative of f with respect to x is going to be, provided that I didn't completely screw this up, it's going to be very similar to our second derivative stuff that we had up top. But the good news is that since we're doing partial derivatives, it makes it a little bit nicer. So yeah, x minus y, we're going to take the derivative of the top with respect to either x or y. We either get 1 or negative 1. And then the derivative of the bottom is going to be a negative 1 times that thing squared. And put in the appropriate either product or quotient rule, we end up with this stuff right here. So we get a 1 divided by 1 minus x minus y minus x minus y all over 1 minus x minus y all squared. And with respect to y, we get a negative 1 over 1 minus x minus y minus x minus y over 1 minus x minus y all squared. Partial derivative of g with respect to x, we drop the x off the front, and then we're left with the constant with respect to x, 2 plus y, and take the derivative of the y portion, which is 2 plus y. We take its derivative, it's 1, multiplied by our constant portion with respect to y, which is x. Okay. And then, when we do 0, 0, what we get for our A matrix is going to be 1, negative 1, 2, 0. And then in order to find the linear system and find all the eigenvalues, we're going to take that and say, all right, do the determinant of A minus lambda I. And that's going to give us what is the determinant of 1 minus lambda, negative 1, 2, negative lambda. We want to know, when is this equal to 0? Because again, we want that determinant to be equal to 0 to show us where the system is going to be linearly independent. So here we end up getting a negative lambda, positive lambda squared, minus a 2 times negative 1. Set equal to 0. We have lambda squared minus lambda plus 2. Yeah, okay, good. So we plug that into the quadratic formula, get a plus 1 plus or minus. Square root of b squared is 1, minus 4 times a times c is going to be 2. All over 2 gets us a 1/2 plus or minus. A square root of 1 minus 8 is going to be a negative 7, so that's I root 7 over 2. Okay, so good news. The real portion of this is positive, which is going to cause the solutions to flow out of our origin point. So we do have, in this case, a source. And it is going to be a spiral because we have a because we do have an imaginary portion. Right. If we repeat at a half, again, we said that this should be a saddle point. So our A matrix is going to be equal to, this is 1 minus a half, negative 1 minus a half. Oops. I didn't entirely explain that, but so here we have yeah, no, that screwed that up. Okay, cool.
No.
Nope, not that. All right, so this is going to be 1 over 1 minus a half is going to be 0. So that gets us undefined. And similarly for the second one. Bottom section, we had 2 plus y was going to be 2.5, and x is just going to be a half. That's 2.5 is 5 halves, and x was a half. So our system around a half should be undefined. All right, Stucky.
Almost.
Yep, no worries. I also didn't do the eigenvectors for 0, 0, but...
Oh no, wait, then I got distracted then.
No, that's all right. Plan? Yeah, no, that was the plan. Okay, so I think also we can see very quickly that our 0, 1 is going to also fail because we have our x minus y up top. That's just going to be either, sorry, that's going to be negative 1 in both of these cases. However, the denominator is going to be 1 minus x minus y is 1 minus 0 minus 1. So both of those are, that's going to end up being undefined as well. And then at 3, negative 2, I think we're going to have the same problem there. So we have a 1 minus x, so 1 minus 3 is negative 2, minus negative 2. So it's also an undefined system. Curses. So none of those are working out terribly well for us at the moment. Okay. Do you have yours set at the moment, or?
I don't believe this answer. But in any case, I do see saddle behavior, since I think we have a positive and a negative eigenvalue, yeah, which is saddle behavior. The directions seem to be a little bit confused right now, but...
Okay.
Oh, I see, and that would be... Okay. Yeah, I think... Something like
right.
This.
Yeah, an 11 to 1 ratio. Yep. I agree. Alright, so eigenvectors are going to be 1, 0, so this is going to be 1 in the x direction, 0 in the y direction. We're just going straight off to the right. And then 1, 11 is going to end up being a... 1 to the right, 11 up.
That.
So, yeah. So if we go back to our picture that we had earlier, right, where I highlighted that particular one. There we go. So at the top right here, we see that, yeah, we kind of have this, let's see, we do kind of have like a horizontal line that our vectors appear to be kind of avoiding directly. And then we also have one that goes kind of this way, although it doesn't quite look like it's in a ratio to 1 to 11, but it's fine. Again, these are all approximations. So if it doesn't 100% line up, it's fine. It's just probably like we need to zoom in a lot in order to see that behavior properly. There's a lot of potential visual errors for this stuff. Oh wait, you did -2, -2. Never mind. It's the other one. One at the left there.
Oh, that's true. That looks a little steeper, yeah.
Much better. So again, this is probably a 1 to 11 ratio, which is going to be like very steep. And then this was going to be flat, which it does line up essentially perfectly. Y equals -2 was our, what was it? X prime equals 0. No, sorry, Y prime is equal to 0. So when we have no change up or down, we're along the line Y equals -2. Yeah, sure, makes sense. And then our, let's see, do we have another thing that was going on? I don't think there was something else going on at that point particularly. Oh no, it was, yeah, vertical. We also had x prime equaling 0 along the line y equals x. So in theory, we should have something that is literally vertical, but our linear approximation is telling us that it's in a 11 to 1 ratio, so it's just fairly vertical. Okay, and then again, behaviors around that, we can see that we had some of our function going like this, and some of our function going like this. Mine is exaggerated because according to this, you have to be like super, super close to the singular point, the node, in order to actually see that behavior. Out here, I think I made it far too gentle. It's still like extremely steep as you get close to those values. Okay. So, right, we found a couple of found at least a couple of places where we do have an good approximation to our system. With the eigenvalues, 1/2 plus or minus I root 7 over 2. This is going to create the system for us. C1 multiplied by, here we have, this is going to be C11, C12. I don't have those values on me, but again, we could do it out. It's just going to take a while. This is going to be e to the 1/2 t for both. And we're going to get a cosine of root 7 over 2 for both. T. Okay, plus C2 for both. That's going to be C1, nope, 2,1 and C22. Times e to the 1/2 t. then multiply by our sine of root 7 over 2t. Right, so this is the approximate solution, our linearized solution around 0, 0. And naturally, we would find C1 and C2, but right now we're just in a little bit of a rush. It's fine. Oh, right, and this is not for all positions, but this is not going to be x and y. For 0, 0, it will be. However, this is U1 and U2. So for the system you found,
Right.
this would actually be x plus 2 is equal to, and y plus 2 is equal to. And we'd have our C1, bottom one is 0, so actually we can just get rid of that. Right, times e to the 1/5 t plus C2 e to the negative 2t, and this was a plus 11 C2 e to the negative 2t. Righto. Questions on that? Comments?
Broadly, how should I think about this method of linearization in relation to Euler's method? So it's not iterative, but Euler's method does have this like linearizing feel.
So I think that
and I'm not sure.
Euler's method is much more a direct linearization where you're saying, I want to take a segment and move it from here to there. And then you're just moving that segment and saying that it is going to be approximately straight between these two positions. So you're using the exact x prime, y prime that come from the original equation, and you're plugging in values to see where that goes, and then just tracing from x0 to x1, x1 to x2, x2 to x3, and similarly for y. What point comes next in the iterative process? The linearization doesn't really do the same thing. This is saying, let's assume that we can find some, U matrix, which is going to be a just space-shifted X matrix, or X vector, where the new x0, y0 becomes our center. And then if it were linearized, if this were a linear system centered around this other point, what values would we get for our A matrix? I've been calling it A matrix. I've been coy about this. It actually does have a name, but sometimes I'm kind of loath to give the name of the thing just because it starts getting loaded and people start being like, oh, well, what do I need this thing for? And memorizing it. And you know how I feel about memorization. But anyway, yeah, so because it's finding a linear system, rather than like trying to trace out values, it's doing something different. I will say that Euler does, given a sufficiently small delta x, or delta t, I suppose, right, in a system, given a sufficiently small delta t, Euler will come up with better approximations, just due to the fact that it will take into account all of the little nuances that exist, because, yeah, sure, you're close to 0, 0, for example, but all of the other parts of the system are still pulling on it, just ever so slightly. So it's still going to affect the answer. This particular method that we did here of linearization doesn't. It just basically says everything that we care about that is close to this particular point is going to be encompassed by this particular linearized system. It is, in theory, possible to start like saying that, you know, each of your individual systems are going to be weighted based on like the distance that you are away from their node, but I'm not going to go there. It's, again,
right.
That's in theory.
All right.
So what we have here, the thing that I've been, again, coy about not calling it by its actual proper name. This matrix here, the A matrix with these special conditions, is called the Jacobian Matrix. Discovered by Jacobi, shock, who was a Polish mathematician from, come on, Arg. Come on. Boo. Carl Gustav Jacobi. Nope, I'm wrong. German Jewish. But it was still mid-1800s. So somewhere between... Where's that? That's the encyclopedia. Cool. Cool. They don't have the history there. Anyway, we used to joke that our linear algebra professor was old enough to have be the Jacobi who discovered this, but sadly that was not him. Yeah, I have mentioned our professor Derek, I think it was Derek Jacobi, got his PhD, quote, in the 40s, and this was 2001 to 2005 when we had him.
Legit.
He had a salt and pepper ponytail that went almost all the way down his back. He was balding. And he used to teach class with his feet on his desk, and his eyes were always very closed because he was just, quite frankly, that old. And he would just like write stuff on the whiteboard without looking, and then occasionally now maybe his eyes were just closed enough that it looked like he wasn't looking. But, you know, he'd occasionally look up at the board and, like, if his marker wasn't working, he'd just stare at it. and throw it over his shoulder. So my spouse is just like cracking up every single day in this class because he's just like so beyond hyper. He just has all these little mannerisms and stuff like that just made her laugh every single day.
Yeah, I can't say I've really had the old professor experience. Maybe Bill. We'd call Bill something similar, but nothing not like that.
Yeah, I was less amused. Just because the problem that I had was she had him first for Linear Algebra 1, which is the sophomore level class, and she got used to him. And then we both took together the same senior level linear algebra class. And I'm trying to correlate all of the old terminology that I learned in sophomore year with all of the new terminology that he's giving in senior year, because unlike every other linear algebra professor who, there is a direct, not only one-to-one correspondence, but literally the same words. So Jacoby decided that he was going to change all of the terminology to like whatever he felt like. I mean, he's a tenured professor, so of course he is. But the way in which he did it was, the point was that it doesn't matter what we call these things. Let's talk about the structures that exist. And I was not appreciative of this particular method of teaching this topic, because linear algebra was my by far weakest of the three classes that went together for linearity. Again, multivariate calculus, differential equations, and linear algebra. So he just made up all sorts of terminology, and I'm just like, I don't understand. Can you please just talk about it in terms of like span and basis and all this stuff that I sort of get, at least? And he was just like, yeah, no. So my spouse got me through that class. And there were some days where I was pretty desperate to skip, and she's like, no. You will not skip. Like, fine. So I showed up every single day, unless I was sick. And then this was our senior year spring. So we get to the end of the semester, and he has us do oral finals. And I'm just like, I am so screwed. So I sit in his office, and he's like, so tell me what you know about a span. And I'm like, and I'm like, I'm so confused about all of the terminology that you use, like with the, and now he's just going back to like, his exam is in the proper standardized mathematical language, and I'm like, I am just done. I don't understand. So we get through the whole thing, and he backs up, and I get a couple of questions right, and he's like, okay, cool, now let's build from there. And we get to the end of it, and I'm just like, and he goes, I think you're getting a B. And I'm just like, it's like, yes. That sounds good. Considering that I was pretty convinced that I was going to get a D. Have to take it over. Take it at a different school or something, whatever. But ended up working out okay. story time. All right, Stucky, do you have any other questions? I think I'll
we're good.
wrap up any other thoughts we have here. So, right, the other question that I had from earlier, if we were to link this back to like power series, is there kind of a word or phrase that you remember that like a series will have a particular behavior within a certain region?
I mean, like a radius of convergence?
Yeah. So normally you have a series which will have a particular radius of convergence. So you look within a particular distance of a particular point. And we say like, okay, if we're on this big thing and, you know, our x is here, we've got 1 here, we've got our power series x minus 1 to the n, whatever we're doing. And n goes from 1 to infinity. Then, you know, we want to know what's the radius of convergence, so we know anything within this will converge. And anything out here will end up diverging. Convert to chicken scratch. Great. Well, when we're talking about this particular system, we do have a fairly similar set of behaviors. Which end up doing, again, something very vaguely like this. Alright, this is going to go like that. This is going to end up going like that. It'll curve in too. I don't know exactly how this is going to look, but roughly speaking, right? Something like this. We had over here a another saddle point, which went like that. This can go that way. This can go that way. That. I don't know that that actually happened up there, but whatever. It's close enough. So we had something that looked more or less like this, and what can happen is we can kind of cordon off each of the segments into like behavioral regions. So much like our radius of convergence, we're saying like anything that's within these particular areas, if you were to pick initial conditions, within these areas, they will have these particular behaviors. So the way that this works is that this ends up being what's called a Basin of Attraction. So anything within a particular area will have this particular behavior. It has a basin of attraction to this behavior within, again, each of these areas. We can either approximate them by finding our linearized system, or we can do our best and try to figure out what's going on with the main system, like the unaltered system. Let's see. Rex talked earlier about chaos theory. And this is actually where chaos starts coming in, where we see that there are sometimes clear, but other times unclear, basins of attraction for any particular behavior. And even a minute change in the initial conditions of a differential equation can end up getting you wildly different results. This is especially seen in like fractals. And Stuka, do you know the curses? I think it's iterative process of taking like 1 plus z to the nth power, where z is a complex number, and like
Okay.
I don't remember exactly. It's like Julian numbers and things like that.
Okay.
Sorry.
Okay.
But if you take a particular, I think it's z plus c, right? Some number c, and then you raise this thing to the nth power, or you just keep going and going and going with this process, then you end up with, like, if you start with a particular c value and then repeat this process, you always end up within certain regions. And this ends up being a crazy fractal that shows us the values of c, which then become what particular solutions. I don't think it's Mandelbrot. It might be. Hi, Noble. How you doing? So 1 plus, or c plus z to the n. No, it is Mandelbrot, probably. Nah, that's fine. I mean, I can't remember what it is, so... Alright, if I just type in Julia set. Z squared plus c, there we go. So if we, let's bump this over here. Sorry to everybody, I just blinded. Right, zooming into a Julia set, complex z-plane, complex valued polynomial function of second degree, p of z is equal to z squared plus c. So all of the different possible c values get you the like different locations on the Julia set. And there is a colorized version which actually shows you like a better, like what values of c will, there, that's it. For what values of c will you end up getting each of the particular different behaviors. So red, green, blue to represent each of the 3 major behavior types. Aperiodic, how's it going? Good evening and welcome. Yeah, I'm not really well versed in this stuff, but we have sort of similar... The point that I was trying to make is that there's sort of a similar idea happening with basins of attraction for differential equations, which also end up being reflected in chaotic systems. So we might, for instance, have a bunch of really weird non-linear differential equations which create wildly different behaviors depending on where you started. I'm going to recommend that everybody look up stuff for the attractors. There are a large number of attractors which do all sorts of different stuff depending on what the need is for that particular math problem. The one that I'm thinking of, fractal patterns. Boo. Nope, that wasn't it. Curses. Wasn't collapse. Come on. Come on. Oh, chaos theory. Yeah. Rössler Attractor. Which has a very basic, like, kind of circular pattern that it has at the bottom. But then when it gets to a particular zone, I think like once it starts getting outside of a particular area, it has a wild jump in the Z direction, and then goes like way to the inside, and then starts circling back outward until it gets out here again, and then it makes this, again, another wild jump. Something like that. And the other one that everybody talks about is this bad boy right here. Where is it? Of course, it's not going to give me the name of it, and it's escaping my brain at this exact moment because I needed it. Anyway, this one. So yeah, that particular attractor is like one of the most famous ones, oftentimes thought of as the more beautiful one because it's similar to a butterfly's wings, which everybody's like, oh, well, it's great that chaos theory gets like the butterfly effect title to it, because you know this attractor kind of looks like a butterfly if you squint.
Yeah.
I don't remember if yeah, I don't know if you know it, Stucky, sorry.
A periodic suggests Lorenz attractor.
Lorenz, yes, thank you. Very silly that it escaped my name, because, like, again, it's... Once it gets large enough, it kind of goes off into this other one over here, and then starts cycling in. No, it'll cycle back out again. It's fine. So it makes a small loop like this, and then starts building out again, and then eventually, once it gets over here, it kind of dips over to the other one and starts making a circle again. So the Lorenz attractor ends up making this nice shape. So there's a bunch of different attractors that we can look at. There's a bunch of different non-linear differential equations that we could pull up and start talking about. We're probably going to look at least a couple next class, so on Wednesday. Most likely going to include a predator-prey model. And I want to talk about the three-body problem and why precisely the guy Dave, who was who worked at APL for many, many years, came up to me and said, "You know, I think you're going to solve the three-body problem," and I just laughed in his face. Not, politely, but I was like, yeah, okay, Dave. We'll discuss why exactly it is that I knew that was not going to happen. Alright, so next class, looking forward to that. Stuki, if you want to plug your channel, if you have any plans.
Not really. Sometime this weekend, usually about 6 hours ago, I'll be 6 to 7 hours ago is when I start. Yeah.
Righto. Sounds good. I hope everybody has a good evening and a good couple of days. I will be back just for, random math help tomorrow, timing permitting, and, family not wanting / needing anything for tomorrow night specifically. And then Wednesday we'll be back for class. Same time, which is 2100 BST, British Standard Time, which ends up being back 5 hours, 1600 Eastern and 1300 Pacific. So if anybody is interested in all of those numbers, there you are. Alrighty, so this has been a periodic. Thank you so much. That's very generous. This has been differential equations, specifically looking at nonlinear differential equations, nonlinear systems, and attempting to linearize them to connect this, at least, get a decent approximation based on what we've been talking about in the last few weeks, which again has been how to, or in the last week, which has been how to talk about systems, first order systems of linear differential equations. Alrighty. So, I think we're gonna head off for a raid. Stuki, thank you so much.
Sounds good. Thank you for having me.
Yep.
For host.
And see you tomorrow / Wednesday.
Alrighty.
Alright. Do we have anybody on for mathematics? I don't see anybody on right this second, however. Stats in the Wild. I have not seen that person. But sure, let's give it a shot. Looking down on you from the ivory tower. That's a good catchphrase. Alright, sure. Let's do it. So, thank you everybody for coming. Let's start this. Get 10 seconds on the clock. And we will be back, like I said, on Tuesday, tomorrow, for random math stuff. We'll decide kind of what we want to do in the moment. And then we will go over to... and then we'll come back on Wednesday for more differential equations class. So, thank you everybody for coming. Thanks so much for the sub. Aperiodic, thank you everybody for following and hanging out and doing all the great math things. We'll see you later. My name is Obi-Wan Pez, and this is N Simplex Pachinko. Have a good night.